this is the way to prevent a child ever developing a fear of algebra. Number two, go back to scratch with this activity and reintroduce algebra from just using numbers. And we're going to show you how to do that today.
Now we have Macy's Great American Marching Band. You might ask, how many in the parade? How many in the band? And if you count the people in red in the front, they seem to be the 10 leaders. And then there's 8 columns, if you look, 8 columns. And in each column, yes, 8 columns. If you were to count the number of people in each column, that is the number of rows across, you could work out how many people. We're not going to try and do it. It's just, I want to talk about really how, if you've got what we call a square array, or if you like a rectangular array, you can do some multiplication to find the total number.
Right. So it's basically, you look at that and you think, oh my goodness, counting all of those, 1, 2, 3, wait, I missed 1, 4, no, wait, start again, 1, 2, 3. That's not a very efficient way of working out how many people there are.
No.
So instead, we have this really cool thing called multiplication, which actually saves us from having to do that because we use our noddles.
You still got to do some counting. You've got to count the number of rows and columns, but that's all. Well, then you've got to multiply the 2 numbers together. Yes. So that's why we put that one in, because this is going to be, the whole session really is going to be about this whole idea of the connection between multiplication and squares and rectangles. Now, with this one, I want you to ignore the way it's colored, but we're just going to focus on area for a minute. And each small square is 1 unit of area.
When I first heard this concept, I was not quite clear because I'd always heard, okay, it's got to be a square centimetre, a square something. This is literally each of those squares, we're calling it 1 unit square. So it really makes life very simple because you can literally count all the squares to know how many square units there are.
Yes, and the reason for sometimes finding it convenient just to define your own unit of area is because you sometimes want to you maybe project your image on a screen or something, and then they'll say, oh, but that doesn't measure 5 centimeters. No, I'm calling that 1 unit. So you know, it doesn't matter. This, as you see, it's one. Well, it's each little square is 1 unit. So if we start with the purple ones at the top, there's 2. So that's 2 square units. And the pink, the sort of peach colored ones, there's 3 there. And now we come round back to our marching band, because for the green, we've got 4 columns and 2 rows. So that's 4 times 2 equals 8 square units. And for the blue, we've got 4 columns again, but this time we've got 3 rows. And so that's 4 times 3 equals 12. But what we're going to do throughout here, why we're calling it Algebrarea, funny name, algebra and area all pushed together into one name, is that the basis of this is going to be often area or algebra or multiplication. So let's move on.
Area or algebra or multiplication, Algebrarea. It's a bit of a mouthful, but it's I find it's quite mesmerizing name. I'm like, I do remember it, Algebrarea. For as long as I can say it, I do remember it.
So we're making connections, which is very important in mathematics. We don't teach things as being separate in their own little compartments. Now we've done that, we'll move on to something else. We try and connect the ideas with all the other ideas to which it's linked.
And that is a really important concept in mathematics, as in life. Anyway, it's a great way to view life in general, always looking for the connections. How can you use this knowledge to help you with this task or this problem?
So now here we come to another diagram. Algebrarea, there's the name again. And we've still got our square divided up into 4 parts. Don't worry about the proportions now. Just believe the numbers.
It's not to scale. It's not
to scale. No, it's not to scale. So we can look at this in different ways. That's what we're going to do. We can take it very simplistically, and we can say there's 4 plus 1 there across the top, and there's 2 plus 3 down the right-hand side, and just as we did with
So this
counting,
is a simple area. 4 plus 1 is the total length at the top is 4 plus 1, which is 5, and the total vertical is 2 plus 3, which is 5. So it's just, so it just makes it, you can see it just looking on the square, on the big square, can't you? It's 5
it's 25.
times 5. Yeah.
Mm-hmm. And we're not now, as we did with the last slide, we're not cutting it up into squares. You'll see in a minute we're going to look at it in a slightly different way. And so what we have got, if we take it piece by piece, we have got 4 times 2. The green was worked out as 4 times 2. The area of the green is 4 times 2. And then the area of the blue,
blue, yeah, the blue
is 4 times 3.
Yeah.
And then the area of the mauvey color is 1 times 2. And the area of the peach color is 1 times 3. And if you add up 8 and 12 and 2 and 3, you get 25 again. So obviously the 4 pieces that you see that divided into will give you an area of 25 in the same way. And well, that's pretty obvious. So you might think, well, why bother with that? But this is a stage of thinking in very simple terms. And you can think back to the last diagram where it was done with squares. And now we're going to do something rather clever with it, which is we're going to change the 4 to 4 tens and the 2 to 2 tens. So it's 40 and 20 now.
And now you can really see that scale doesn't matter because the shape hasn't changed, but the numbers have.
Yes, so we didn't want to match, to show this with drawing it to scale. We wanted more it to be a symbol for the long multiplication, 41 by 23. So it's 4 tens and 1 unit multiplied by 2 tens and 3 units. And you're doing the same thing as we did before, but now we're doing it with tens and units, and we have to bear that in mind. But the arithmetic is easy because we're only multiplying single digits numbers together. So we've got 40 plus 1 times 20 plus 3, but when we think of it, we're only multiplying the 4 by 2 to get 8, but we've got to bear in mind that it's 40 times 20, so it's not 8, but 800. And then we're multiplying the 40 by 3 to get 40 times 3 is 120. And then we're multiplying 1 by 20 and 1 by 3, and adding them all up, we get the answer 943. So this is a lot.
Working out how much each rectangle is on that inside that square, or and then that's no longer a square, of course. That wouldn't even be a square. That would be a rectangle, and then just adding them together.
That's right, and it's all what you're actually doing is using area in a sense, but not explicitly. This is a method for multiplication, and now you're using place value. So you've got tens and units, and you could extend this and you could do hundreds, tens and units, or even four-digit numbers.
And that's a good point. When I was talking about, I said it's good for algebra, it's good for area, but it's also good to think about place value. It's a very effective way to think about place value, isn't it?
Yes, and I think the children can understand what they're doing here. You can take it piece by piece. They're never doing lots of multiplication. They're taking care of the magnitude, the using, you know, the place value, and they're doing it not just with an algorithm, which is, well, maybe meaningless, but with something that you can talk about what this means, what each little piece and each color is showing. But this is general. You can have A and B as the measures along one edge, and C and D as the measures along the other edge. And then we're sort of getting into algebra, really, but it's simple. And in algebra, when we sort of writing down A times C, if we're using letters, we just write AC. And BC means B times C. AD means A times D, and BD means B times D. So we're just using this, not really algebra. It's not really algebra. We're not doing algebra yet. But what we are doing is using these letters and trying to emphasize that the letters can stand for anything at all. In fact, it could be A, girls, the number of girls, and B, the number of boys. And C could be that in the band, whoever was being counted there is playing cymbals, and the D could be D drums. So the number of girls who are playing cymbals in this band is AC. The number of boys who are playing cymbals is B times C. The number of girl drummers is A times D. And the number of boy drummers is B times D. So all we're doing there is really, all we're doing is just using the A's and B's and C's and D's to be anything we like. But we do have, this is algebra, I suppose, but I hope it's a simple way to introduce the algebra, how you've got A plus B times C plus D, A plus B along the top, C plus D down the side, is AC plus AD, and then add BC plus BD, and you've got it.
Yeah,
so,
I think it's a very nice progression, especially when you describe it as something like girl cymbal players. So you've got girls and you've got the cymbal players, and girls and cymbals you put them together to make girl cymbal players. It's exactly the same thing.
So that's not strictly multiplication to have girl cymbal players and boy cymbal players.
No.
But the point is that the labeling is just a way of, we want to tell everybody that we could use these labels very flexibly. Here you see a spiral ramp, and it's going round and round, and people are going up, and as they go up, they come to a point which is above somewhere that they were some time ago. And I've used this as a picture to illustrate what I think learning is all about. There's always more to learn. Our learning experience is like being on an infinite spiral ramp that goes round and round, on and on, forever and ever. Well, from the time we're born to the time we die, at least. I suppose we could say we're not going to learn anymore, but that would be a dull life. And what do you think, Caroline?
I've been working with Toni quite closely. I have had to think a lot over the last few months, and it's very stimulating. I find it's invigorating to continue learning and not become complacent.
But even if you're an expert on something, and we're living in the middle of a pandemic, and thank goodness we've got experts on epidemiology, medicine, and statistics, and they are learning. When this was a new virus, they had to learn about it.
And quickly.
Yes, and they helped each other to learn, and they have produced a vaccine. Isn't it wonderful? And they are helping the rest of the population to understand some of the complexities about it. So if you want to say, well, I'm going to stop learning, I've left school now, I don't need to learn, you won't get very far in life. And what Caroline was just saying is also, I think life would be very dull. So imagine you're on that spiral ramp. And of course, it starts when you're born, maybe even in the womb, and then you build on it. So we're going to talk about the school now. Now, I want you to imagine these are phases in school, you know, preschool, primary, lower secondary, upper secondary. But you might leave school with A stars in all the exams, but you don't reach a platform there at the top and say, no, I'm done. That's good. I've learned all, I've been at school now and I'm about to leave school and I know no, you don't. The ramp.
I know it all.
The spiral continues for the rest of your life, as we've just been talking about it. But I'm using this slightly different diagram of a spiral ramp because I want to talk about Algebrarea, which we were talking about before. And I want to talk about how we start with the basics for very small children, preschool, understanding the basics of rectangles and area. And we're going to go into more detail a bit later about how to do that. But even preschool, we're laying the basics of some of these ideas. And then the next stage is the connection between counting squares and multiplication, or in the band, for example, counting the number of columns and the number of rows and the number of people, so that the multiplication. That's the next connection, but with very simple numbers to start with. And so you realize now that you can count the number of elements in a rectangular array by multiplication. But now you're in school, maybe you're 6, 7, 8 years old by now. But you maybe have to go back to something that you did last year to try and remember and build on that. But now you're going back up. And next thing is to understanding the nature of multiplication as repeated addition. For example, in the band, we saw that there were 8 columns. So when you were seeing how many people there were all together, it was 8 plus 8 for the next row, plus 8 for the next row, plus 8 for the next row, plus 8 for the next row. And the very old-fashioned calculating machines, I remember using a Brunsviga one when I did some office work as a teenager, where you had to turn the handle one way for addition, and you turn the handle the other way. Nothing electronic there. You turn the handle the other way for subtraction. You really understood when you used that machine that multiplication was repeated addition. And then there's a connection to multiplication and area, where we multiplied with the marching band the number of rows by the number of columns. And then going on, we saw this a few minutes ago. We saw long multiplication. What was it? 41 by 23 using place value, but using the same principle. So you see, these are like the layers of knowledge, but they're deepening the knowledge, and you won't really understand at the latest stage if you hadn't built a good sound foundation and been building on it year by year. And of course, what's applying to multiplication and algebra and area applies in all sorts of topics in mathematics. Mathematics is very much a subject where you can't start something new and not need to know anything that you should have learned in the past. It's always building on something. And that's, I think, why people find it difficult, because sometimes that basic knowledge is not there.
Yeah, if you've got that foundation missing, the house is going to collapse. So, but it isn't hard to regain that, because I do tutoring and I have experienced that. I'm sure you have as well. It's like once you've filled in the foundation, us being humans and learning machines, it's a relief at how quickly you can get back up to speed to where you're supposed to be, to understand the level at which you're being presented at school.
Yes, and I think that's very reassuring, because everybody forgets things. We've got various devices in the Aimsec method to help children to recall what they learnt by themselves, not listening to the teacher yet again saying the same old things, but matching cards. And well, we'll show you some of these methods so that the children work it out in practical ways to refresh their memories, to help to remind each other, perhaps doing it in a group, reminding each other. So the top of the list that we've got now, because we're working our way up, is this application to algebra. So now we're coming into secondary school, and all of these stages that we've been building on in primary school, we now begin to apply this to algebra. And so up we go, and then it's simplifying algebraic expressions and multiplying expressions and solving equations, and more. So as we've just been discussing, we're adding, it's a bit like onion skins. It's certainly layer upon layer upon layer, and building a nice, strong, deep understanding of a well, not just one subject, but a lot of different related concepts. Okay, we're going to talk about laying the foundations of learning with very young children. Now, it's very interesting that one of the countries in international comparisons, when people do research comparing attainment of children in different countries, one of the countries that comes out on top, very near the top, is Finland. And they have a philosophy about children and about learning, and that is that play is perhaps the most important thing, that children learn best by playing with ideas, and by not just with ideas, but being free to play in their own way. And in fact, they don't start school until they're 7, I believe, in Finland, whereas in the UK, children start in the year in which their 5th birthday occurs. So almost everybody in the class is 4 at the beginning of the school year, and then they have their 5th birthday in that first year in school. We do call it reception class, but they're in big school rather than a nursery or preschool. But the Finns actually do extraordinarily well with this idea that you don't have to have as many hours of lessons. Let the children play. And I think it's very important that we remember this with young children. And so this is a puzzle, but it's something you can make with cardboard. We've given you the template for it, so you could use it and maybe stick it on the paper on some cardboard and cut the pieces out, and then you've got something to play with. We're going to get involved, aren't we, Caroline, with a publisher who's going to not just publish books, but actually the pieces for games and puzzles, and then people will be able to buy a nice plastic set, or even a wooden even a wooden set, which is even better. But anyway, we're suggesting you do this with card. You make these pieces all the right size, and all the blue pieces of the 2 squares the same size as each other. The green pieces are squares again, and the peach-colored pieces are rectangles, but the dimensions, how they relate to each other, are quite important, and we'll come back to that. But start with free play and say to the children, what can you do with these pieces? Let them play with the pieces. They might stack them, they might sort them. There's all sorts of ways. And talk about the shapes and the colors. They should learn the names, but it's not something you want to force on them. as they're learning other language, they can learn the name square and rectangle. And you might ask, bringing counting into it, how many pieces have you got? And they might count, there's 2 blue ones, and there's 3 green ones, and there's 5 peach colored ones. So they're learning about colors, they're learning about shapes. And by handling them, they're realizing that the corners fit one on top of each other, and they're square corners, and it's like the corners of a room, and you can fit 4 of them round a point. And there's so many things that you're not going to make explicit. You're not going to try and explain to the children, but they'll get a feel for it just through play.
And the green ones are smaller than the blue ones. That's something that they'll notice.
And talking about, yes, smaller and bigger, that's another good thing to be doing, comparing size. Yes. So.
And are they the same shape? Are the blue and the green the same shape? Are the blue and the peach the same shape? And what, if they're not, what is the same and what is different?
Lovely questions. What's the same and what's different? Now, you wouldn't come on to this formal task that we'll talk about in a minute. You wouldn't come on to that the first time. You'll have spent many, sessions or hours or a few minutes here and a few minutes there on free play with these pieces. And then this is the formal task. This is, can you fit all those 10 small pieces into the frame, the big rectangle at the top? Okay. Well, it can be done, but it's a puzzle. Like any jigsaw puzzle, you have to experiment and try whether this piece fits there and how you put the pieces together. So it's not like a jigsaw puzzle with a picture on it, where you've got these sort of knobs that fit into sort of harbour-shaped bays. But you know what jigsaws are like. This is different. You might show them how the pieces fit in and then take them out and mix them up and say, now can you do it? So they realize what the aim of the game is. But that's up to you and your child. But the idea is that they play around with them. And what they have to realize is that the edges must be made to match, as you see the peach rectangle and the green square there. Those edges have to be the same length so that you can match them together. When you fit them into the frame, they must be made to match like that. And here you've got the green edge doesn't match the longer edge of the peach piece, because you've got to match 2 edges of the same length. But I think if you try and match the peach rectangle, you'll find the longer edge matches the blue square. So that's beginning, once you realize that, that's something that you're using when you fit them in to the puzzle. So it's not an easy puzzle, even though there are only 10 pieces. You do have to experiment with it to actually solve it. But it's something that a 5 or 6 year old preschool can do, or you can do it with them and then do it many times. Take the pieces out of the frame, mix them up, and see if you can do it and remember how to do it. So that's your play. And what you're learning here is, we called it the basics, the ideas of shape and area, bigger and smaller, things fitting together. Now,
and also observation, you're learning to observe and to differentiate, look at the distinctions between the different shapes.
Now, we are coming around again in the next year or 2, 3, once they're in what the children often call big school, you're coming around to the same task, the same puzzle, but you're doing more things with it. So you might say to the learners, everything we were talking about with the younger children, you'd certainly give them some time for free play. You certainly talk about the colours and the shapes and the names of the shapes and what's the same and what's different about them. And even though they've done it before 2 years ago, they come to it again and think about these things. They may make other observations and have a much more sophisticated or developed language in which to talk about it. And you can ask them how many other shapes they can make with the 10 pieces matching them edge to edge. So they're going to do the puzzle, but they may be able to fit the pieces edge to edge and make not a rectangle like we were doing in the puzzle, which was fitting them into this frame, but make an L-shaped piece, or maybe just a piece that's not anything that you would give a name to, but it's a composite piece made with these 10 shapes matched edge to edge, as we've described. And then ask them to draw the shapes that they make. Now, what we're building up here is an idea of what we call conservation of area. It means that you don't, by moving these shapes around and rearranging the patterns, each one keeps its same area. And when you put them all together, the area of all 10 of them adds up to the same area, whatever configuration you make. It's a pretty fundamental idea. I mean, if you take a liter of water and you pour it into a bucket, it's still a liter of water, exactly. Well, you might spill some, but you know what I mean. The idea is that changing its shape and well, that actually would change its shape, whereas these pieces, you don't change the shape at all. They're not made
not of the piece itself, but you can change the shape that they make when put together.
The composite shape.
And the other thing that doesn't stay the same is the perimeter.
Exactly. So the area stays the same, but the perimeter will change. Yes, that's absolutely right, Caroline. What a nice way to think about it. Yes.
And it's a lovely observation for the learners to realize that and play with it and measure the perimeter to see, okay, so the area does stay the same. You've got the same squares and rectangles, but how can we make the longest perimeter? How can we make the shortest perimeter? And how many different ways can we do that?
That is a nice idea, Caroline. I mean, I hadn't thought of that myself, but I do like it because the way area and perimeter are taught, I find that even secondary school students often muddle them up. They don't know which is which. And I think the more experiences they have when they're younger and talk about the two different things and what is, perimeter isn't the same as area, If they've got a school yard, there's usually a fence around it. Well, that's the perimeter, and it's not the same as the area in the yard that they play on and run around in. And, it's that sort of analogy that you can use. And as Caroline said, they can put these pieces together and make different shapes with them and draw them and measure the area, measure the perimeter and see that the area stays the same and the perimeter changes.
You have to give John Mason the credit, Toni.
Oh, yes. So now what we've seen is, in the last few minutes, we've seen how you would start with 3- and 4-year-olds playing with the shapes, and how the lower primary 5-, 6-, 7-, 8-year-olds will do a little bit more with them, and how you're building all these different ideas we've just been talking about. With upper primary, I would ask the children, give them a sheet with them printed on and ask them to cut out the shapes. and to solve the puzzle by fitting the 10 smaller pieces into the large pale green rectangle and sticking them in place in their workbooks. So now it may take them quite a while to do this, but what we're emphasizing here is really that it's a puzzle, and it may not be very easy, but they've got to persevere, and they should be able to do it. And that we're using X units here to compare these edge lengths. That the edge lengths of the blue squares is the same as the longer edge of the peach rectangles, and the shorter edge of the rectangle is the same as the green, the length of the green square there. And there's a lot they can do talking about the different shapes, and then encourage them to experiment by drawing their own, making other configurations and drawing their own shapes, matching the pieces edge to edge. And they should draw them and write down their areas in square units in terms of X now. So now we're taking it a little bit further. So they'll be now looking at the area of the blue squares. What are they? Well, it's X times X, and it would be true whether X were 529 or whether X was 0.0529 or whatever X was, that you would multiply the X by X to get the area of the square. That would be square units. Now we hark back to multiplying numbers to do multiplication and counting, and you can do long multiplication that way. And we're now just edging into algebra, and it doesn't matter what X is. We're generalizing now with these children that the idea is we're just writing it in terms of X, and look, whatever X was, the area of the blue square would be X times X, square units. So we're not actually doing algebra, are we, Caroline?
No, we're just saying what the area is of each rectangle or square.
Yes, and it's a name really, like your name's Caroline and my name's Toni. But yeah, actually...
And then all we need to do is add those all together.
Yeah, but of course you're unique and I'm unique. The point is about X. X could be anything. X is a variable, actually. We don't need to use that word, but I mean, it is. Now, there's another subtlety here that we've realized, we should have realized when we were, now we're not talking about the marching band, we're more talking about the experience that these children have had in primary school so far. They will have done multiplication of numbers like 41 by 23 by seeing these as 4 parts in a square that they multiply together, the edge lengths together, and they use the place value tens and units, and they get the answer to this long multiplication. They'll have seen that. So what we're coming back to now is same sort of idea, but we've sort of got connections with what we've done earlier. And we're now talking about area. And now, what about the area of a peach shape? What would that be?
It's X times 1.
But
oh, wait.
Yes, you're right. Of course, you're right.
That means there's only one X, so we can call it, we can simplify it. We can just call it X.
Yes, but it's X square units once you're into area. So I think this is something.
So but it's X square units.
It's x square units.
It's not x squared. We've got to be very, very clear on that point.
So just like when we're actually measuring in centimeters, if our units were centimeters, then it would be square centimeters for area. Or if we're measuring the playground, for example, we might measure it in meters. So we will be measuring it, the area would be in square meters. So we'd measure the fence in meters and the area in square meters.
I could see this as a point of confusion here, though, because you could say, because x times x is x squared. So someone could say it's x squared units, but it's not. It's x squared square units. So if we want to call them centimeters, it would be x squared square centimeters. So the number would be x squared, and the units are square centimeters. So this is x squared square units. So you've got to be very clear about that.
You do,
and that's just to prevent misunderstandings, prevent that foundation from falling down from under them when things get more complicated.
Yes. So I wouldn't push the algebra too much here. I would be saying, no. Suppose it was the blue edge was 7 units long, then what would the area be? It would be 7 times 7, which is 49 square units. So at primary school, we're not really getting into algebra. It's really pre-algebra.
But
so
you do want, but it is important to emphasize that it is square units. So when it's a line, it's units. When it's square units. And when they get to volume, it's units cubed or cubic units. And it's really important that they're clear on that point, because that is a point of confusion, and it's something that gets missed.
Yes,
because it's not within their experience beforehand.
That's right. When they're in secondary school, quite soon they'll be learning to write the little numbers in the air up on the right-hand side, for x squared meaning x times x, and for x cubed meaning x times x times x. But that's not where we're going at. It's important to keep using numbers so that they feel comfortable with it. So supposing x is 7, then the blue square is 7 times 7, 49 square units in area. And the peach rectangle is 7 times 1, which is 7 square units in area. And the green square is 1 times 1, so that would be 1 square unit. Now, they're not drawn to scale. We're just using these examples.
Well, you're not drawn according to that scale, but those rectangles and squares are drawn, so you can cut those out and join them. It's just that the numbers that Toni was using are not the scale, but that is an active puzzle.
I think that the actual ratio is something like x is like 1.5. If they were, if they were drawn to scale, x would be something like perhaps 1.5 or 1.4 or something like that ish. There's lots more you would do, and so we do have a website called Aiming High, and for this Algebrarea there are many different tasks, and we've just chosen to dwell on one of them while we're talking now. But if you go to the Aiming High website and look for Algebrarea, that's a package. It's a learning package with lots and lots of things in the package. And we'll talk more about this next week, because we haven't got into secondary school yet on our ramp. We're only about age 11 now, maybe different countries, of course. Don't be too worried about me referring to age, because different countries have different school systems, and they change from primary to secondary at different ages. But South Africa has a very odd system where they've got secondary children in year 7 defined as secondary, but actually all of them still in primary school, which is a bit weird, isn't it? Because they don't go to secondary school until they go in their grade 8. So don't you worry about these ages. if you are a teacher, then you know, or a parent, then you know what your child is capable of, and you choose what's suitable for them, and don't worry about what there's not an age label really.
And the great thing with these is that if someone has didn't catch something, and there is that foundation missing, you can go back and use these activities to build that foundation back up again, so that they're back up to speed with what is expected of them in school, and just keep building it up. And if you don't know, do it with them and learn together.
With your children.
It's really powerful, so powerful if you learn with them. They learn to respect learning by doing that.
So Caroline, would you like to talk about Aimsec?
I would love to talk about Aimsec. It's my favorite. This is my cause. I do fundraising. I've climbed Mount Kilimanjaro for Aimsec, and Aimsec needs funding, help. Basically, what they do is they provide professional development for teachers who teach they provide professional development for all teachers. So the courses are available if you wish to learn this way of teaching. But what Aimsec, the reason why we're donating to Aimsec is that they have bursaries for teachers who work in disadvantaged areas. So they work with poor children with huge classrooms, as you can see there, and in disadvantaged communities. So they don't get paid very much themselves, because that's what the budget's like. But they're very dedicated men and women, and for the money that we raise goes to bursaries so that these people can learn more powerful ways of teaching mathematics and go back and influence thousands upon thousands of children. And the even more exciting thing that Aimsec does is that it isn't just any basic courses. There are layers of courses. Guess what? Spiral learning. And what comes out at the end is teachers who have become, over the years, it's been going on for more than 15 years now, become subject leaders, become subject advisors who work in their region, helping to facilitate maths training with other teachers. And it's a movement, and it's having a huge impact, going from a school that could never had a child going to university to it just being a normal thing that children, not all of them, but they have children going to university every single year, thanks to the courses that Aimsec provides. So if you can donate, actually I should put that link on there, which is now just disappeared.
Any small amount is so appreciated, because a few small donations, it soon adds up. And as you see Mandela at the bottom there, just if you're looking at the picture, Nelson Mandela, he said, education is the most powerful weapon which you can use to change the world. The idea is to give children a better chance in life by giving